Hello friends, I welcome you in lecture number 14 on complex integration. In this lecture we are going to discuss this question which was asked in GTU Summer 2021 examination. So let's see with the circle mod z equal to 2, that is circle with center origin and radius 2, and C is described in the positive sense, that means direction is counterclockwise direction. Evaluate each of the following integrals. So we have to evaluate all these three integrals along this contour C mod z equal to 2. So in all these three integrals, common part is contour. So given that C is nothing but mod z equal to 2, that is, it is a circle with center 0 and radius 2, and we have to evaluate each of these three complex integrals along this contour mod z equal to 2. So we evaluate all these integrals one by one. So in the first part, our function is cos z over z times z square plus 8. So we know that this function cos z divided by z times z square plus 8 is division of two analytic functions. Cos z is analytic everywhere, and this function z times z square plus 8 is also analytic everywhere because it is a polynomial. So this cos z over z times z square plus 8 will be analytic everywhere except at those points at which this denominator becomes 0. So is analytic everywhere except points z, except those points z for which we have z times z square plus 8 becomes 0. So if we solve this, we have z equal to 0. Another possibility is z square plus 8 equal to 0, and z square plus 8 equal to 0 can be rewritten as z square equal to minus 8, and if we replace minus 1 by I square, we have z square equal to 8 times I square. So therefore z equal to plus or minus square root of 8I square. So that means z equal to plus or minus I times square root of 8, and 8 can be written as 4 into 2, and square root of 4 is 2. So finally we have z equal to plus or minus, here we will have 2 times root 2 and into this I. So if z is plus or minus 2 root 2I and z equal to 0, then this denominator becomes 0. So this function is not analytic at point z equal to 0 and z equal to plus or minus 2 root 2I. Now our contour is mod z equal to 2, that is circle with center 0 and radius 2. So suppose this is the circle with center 0 and radius 2. Okay, this is just rough sketch for understanding. Suppose this is the circle with center 0 and radius 2, and it is described in the positive sense, that is counterclockwise direction. This is x-axis, this is y-axis. So this function is not analytic at z equal to 0 and z equal to plus or minus 2 root 2I. Now 2 root 2 is always bigger than 2, so it will be outside this circle. Suppose it is somewhere here, and minus 2 root 2 will also be outside this circle, and z equal to 0 is inside this circle. So if we want to use that Cauchy integral formula, then if we recall what Cauchy integral formula says, that if we have this type of integral f of z over z minus z0 dz, where this f of z is analytic everywhere inside and on this simple closed contour C, and this z0 is interior to this simple closed contour C. If f of z, this function in the numerator, is analytic everywhere inside and on this simple closed contour C, and if this point z0 is interior to this simple closed contour C, then value of this integral is 2 pi I times value of this function f of z at point z0. So here we can use this Cauchy integral formula. For that we have to observe this function cos z over z times z square plus 8. So we will try to write down that function in this form first, and then we will decide what we should consider as z0 and what will be our function f of z. So now if we observe this function cos z divided by z times z square plus 8, then this function we can rewrite as cos z divided by z square plus 8 and divided by z minus 0. Now if we take f of z equal to this function f of z divided by z minus 0, where f of z is cos z divided by z square plus 8, then this function f of z is not analytic if z square plus 8 equal to 0, and that we have seen if z is plus or minus 2 root 2 I. Now plus or minus 2 root 2 I will be somewhere here, because this radius is 2, we have 2 I here, so 2 root 2 I will be somewhere here and minus 2 root 2 I will be somewhere here. So these both points where this function is not analytic cos z over z square plus 8 are outside this simple closed contour C, and this function is not analytic at these 2 points only, but these 2 points are outside the simple closed contour C, which is mod z equal to 2 here. So we can say that this f of z equal to cos z over z square plus 8 is analytic everywhere inside and on given contour, is analytic everywhere inside and on C, which is mod z equal to 2, and we can observe that this 0 lies inside C. So we have written our function as f of z over z minus 0, where f of z is analytic everywhere inside and on this simple closed contour C, and this point 0 lies inside C. So we can apply Cauchy integral formula, and 0 lies inside this contour C. So therefore by Cauchy integral formula, integral of f of z divided by z minus 0 along closed contour mod z equal to 2 will be equal to 2 pi I times value of this function f of z at point z equal to 0. Now f of z is cos z divided by z square plus 8. So if we put z equal to 0 here, we have cos 0 divided by 0 plus 8. Cos 0 divided by 0 square plus 8. Cos 0 is 1, and we have 2 pi I times 1 by 8, and this becomes pi I divided by 4. Now we substitute value of f of z here. F of z was cos z over z square plus 8. So we arrive that integral cos z over z times z square plus 8, value of this integral along mod z equal to 2 is pi I divided by 4. So this complex integral we have evaluated using Cauchy integral formula by taking f of z equal to cos z by z square plus 8, which is analytic everywhere inside and on this simple closed contour C, and 0 lies inside that circle. Okay, fine. So now we come for this integral e raised to z over z square minus z minus 20. So now we try to evaluate that second part, integral e raised to z divided by z square minus z minus 20 dz. Contour is same, mod z equal to 2. Now we can see that this function is also analytic everywhere except those points at which denominator becomes 0. So is analytic everywhere except those points z for which this part becomes 0, that is denominator becomes 0. So we can find out solution of this equation. We can rewrite minus z as minus 5z plus 4z minus 20 equal to 0. Here we can take z common, so we have z minus 5. Here we can take 4 common, so we have z minus 5 equal to 0. And now we can take z minus 5 common, so z minus 5 times z plus 4 equal to 0. So the points where given function is not analytic are z equal to 5 and minus 4. So this function is not analytic at z equal to 5 and minus 4 only. Now our contour is mod z equal to 2. Okay, so let me sketch again. Suppose this is mod z equal to 2. So this distance is 2. This is x-axis, this is y-axis. So this is our contour mod z equal to 2. Now function is not analytic at z equal to 5 and minus 4. So z equal to 5 will be outside somewhere here, and z equal to minus 4 also, because this is minus 2, it will be somewhere here. So this function is analytic everywhere inside and on this contour mod z equal to 2, because z equal to 5 and minus 4 are the only points at which this function is not analytic, but those 2 points are outside this contour. We can observe here this 5 and minus 4 are outside this contour mod z equal to 2. So that means given function is analytic everywhere inside and on this simple closed contour C. And we know Cauchy-Goursat theorem. Cauchy-Goursat theorem says that if given function is analytic everywhere inside and on simple closed contour C, then integral of that function along that contour is 0. So here we can write that f of z, or we can directly write given function. So these two lie outside C. The points at which given function is not analytic are outside this simple closed contour C. So therefore we can say that e raised to z divided by z square minus z minus 20 is analytic everywhere inside and on simple closed contour mod z equal to 2. So therefore by Cauchy-Goursat theorem, integral of this function along this simple closed contour is 0. Z square minus z minus 20 is 0. So in second part we are able to evaluate the integral using Cauchy-Goursat theorem. Now we come towards last integral. It is e raised to minus z over z minus pi I by 2 whole square. So let's try to evaluate that function, that integral. So last one is e raised to minus z divided by z minus pi I by 2 whole square. Contour is mod z equal to 2. So let me check again. It is e raised to minus z divided by z minus pi I by 2 whole square. So here also it is obvious that this function e raised to minus z is entire function, it is analytic everywhere. Z minus pi I by 2 whole square is also analytic everywhere because it is a polynomial function. So this function is not analytic at those points at which this denominator becomes 0. So z minus pi I by 2 becomes 0 if z equal to pi I by 2. And we know that this z equal to pi I by 2, if we find out modulus of this z equal to pi I by 2, modulus will be pi by 2 and it is less than 2. So this z equal to pi I by 2 is the point at which this function is not analytic, and that point lies inside mod z equal to 2 because modulus of this pi I by 2 is less than 2. So here we have to apply again Cauchy integral formula, but here power of z minus pi I by 2 is 2. So we have to apply extended version of Cauchy integral formula. We recall that extended version of Cauchy integral formula is f of z divided by z minus z0 raised to n plus 1. This is equal to 2 pi I divided by n factorial and value of nth derivative of f at point z0. So where we require that this function f of z is analytic everywhere inside and on this simple closed contour C, and z0 lies inside this simple closed contour C. So here we can compare f of z, we will consider as e raised to minus z. It is analytic everywhere. Z0 will be pi I by 2 and pi I by 2 has modulus equal to pi by 2 and which is less than 2. Therefore pi I by 2 will be inside mod z equal to 2. So hypothesis of Cauchy integral formula is satisfied here, and if we compare with power, then here we have 2 equal to n plus 1. So n will be 1. That means we have to consider first derivative. So with this in mind, we try to evaluate this integral. So here we consider f of z equal to e raised to minus z. Let f of z equal to e raised to minus z, and we can roughly sketch mod z equal to 2. It is not necessary to sketch this contour. This is just for understanding, otherwise it is not necessary. So suppose this is mod z equal to 2. So here I will have 2i, and this pi I by 2 has modulus less than 2. So let's assume that it will be somewhere here. Okay, we are not sure about the location, that we can find out by considering pi by 2 equal to 3.14 by 2. But what we are interested is pi I by 2 has modulus which is pi by 2 and it is less than 2. That means it is interior to this simple closed contour C. So we are interested in the fact that whether pi I by 2 lies inside C or not. So pi I by 2 lies inside this simple closed contour C, and this f of z equal to e raised to minus z is analytic everywhere inside and on this simple closed contour C. So we can write that clearly f of z is analytic everywhere inside and on simple closed contour C, which is mod z equal to 2, and pi I by 2 lies inside C. So therefore by Cauchy integral formula we must write all these things systematically, otherwise we will not get full marks. So by Cauchy integral formula, integral of f of z divided by z minus pi I by 2 whole square dz along contour C will be equal to 2 pi I divided by 1 factorial and first derivative of f at point pi I by 2. So now this is going to be 2 pi I, 1 factorial is 1. Our function is e raised to minus z, so its first derivative is e raised to minus z times minus 1. So it is minus e raised to minus z. So we substitute pi I by 2 here. We are interested in the first derivative at pi I by 2. So we take z equal to pi I by 2. So we will have minus e raised to minus pi I by 2. So minus e raised to minus pi I by 2, and here this is negative 2 pi I minus this e raised to minus pi I by 2 is cos pi by 2 minus I sin pi by 2. Okay, we are using this formula, e raised to minus I theta is cos theta minus I sin theta. So here theta is pi by 2. Cos pi by 2 is 0 and sin pi by 2 is 1. So we have 0 minus I, and finally we have minus 2 pi I times minus I. Negative negative will be positive, and we have 2 pi I square, and because I square is minus 1 we have minus 2 pi. So therefore we obtain that f of z was e raised to minus z, z minus pi I by 2 whole square. Value of this integral along mod z equal to 2 is minus 2 pi. So these are easy questions on Cauchy integral formula and Cauchy-Goursat theorem. We can see in all the integrals our contour was mod z equal to 2. In first part our function was cos z over z square plus 8, and we have applied Cauchy integral formula, and this 0 was inside this contour. In second part our function was analytic everywhere inside and on this simple closed contour. So by Cauchy-Goursat theorem we proved that value of this integral is 0. And here we again apply Cauchy integral formula with f of z equal to e raised to minus z. So in all these problems we can remember this Cauchy integral formula, f of z over z minus z0 to the power n plus 1 dz along simple closed contour C is 2 pi I divided by n factorial. Value of this f of z, nth derivative of this f of z at point z0, and n can take values 0, 1, 2, 3 and so on. For n equal to 0 we will obtain this f of z over z minus z0 dz will be equal to 2 pi I times 0 derivative, that means value of function at z0. So here in both the cases we assume that our function f of z is analytic everywhere inside and on this simple closed contour C, and z0 lies inside this simple closed contour C. And we have applied Cauchy-Goursat theorem. Cauchy-Goursat theorem says that if function f of z is analytic everywhere inside and on simple closed contour C, then integral has value 0. So this is all about this lecture. I hope you like it. Thank you very much.